All right, welcome to part 2 of characteristics of rational polynomial functions. For the next example, same as before, we are going to identify the x-intercepts and the points where the local maximums and local minimums occur, or local maxima and local minima. Again, for these questions, you want to use the graphing calculator once you get to the local maximum and local minimum question. One thing we can figure out right away is what our x-intercepts are. So you would want to set g of x equal to 0. And then you can set both of those terms equal to 0 and solve. The 2, if you want to eliminate it, you can by dividing both sides by 2. And then set both x minus 1 squared equal to 0 and x minus 4 equal to 0 and solve. Take the square root of both sides. So for us, we're going to get our first answer is x equals 1. But it was originally x minus 1 squared. So this is going to be an example of a double root solution. And we can show what that looks like in just a minute. So we have x equals 1 and x equals 4. So we can plot those points right now. And a double root solution will touch the axis, but it will not cross. So we will touch the x-axis at the point 0, 1, but we're not going to cross over. We also need to find the local maximum and local minimum. So again, I'm going to pull up the graphing calculator for that. Type in the function that we were given, 2 times group x minus 1 squared times x minus 4, and then go ahead and graph. So for us, see how it touches the x-axis at the point 1, 0, but then it doesn't cross. That's because that's a double root solution, and that will happen with any double root solutions. It will touch, but it will not cross. Our other x-intercept was the point 4, 0. There it was just the one solution, so that's why it crossed there. So our job is to figure out two things, local maximum and the local minimum. So I'm going to go ahead and hit the second key, hit calculate. And then it doesn't matter which point you calculate first, you can calculate the maximum or minimum. I like working left to right, so we'll calculate that local maximum first. And then for the left bound, you want it to be lower than your maximum on the left-hand side of the maximum, but you want it to be close, so I'm going to hit enter. And then I'm going to scroll over until it looks like the tool is going back down, the cursor. And I'm going to hit enter because now it does look like it's going back down. And then hit enter one more time to estimate what the local maximum, what the local minimum are. So for this one, it says the maximum is 0.999996. No matter where you round that, that's going to round to an x value of 1. And then with y, it gave us a negative 8.55 e to the negative 13th. So that's like saying 0.0013 zeros and then 855. So basically another one where when you're rounding it, it's 0. So even though the calculator didn't give us the exact number, we can tell that the maximum here is 1, 0 because of the significant digits we were given. So the local maximum is going to be 1, 0. Then we're going to calculate the local minimum. Exact same process. I'm going to hit clear, second, calc. It's just this time we want to select minimum instead of maximum. Get very, very close to that minimum point and hit enter. keep going, and then once you turn around and start going back up, you can hit enter again and then get an estimate. So here again, 3 point, a whole bunch of zeros and a 5. That's probably 5, but just due to rounding and estimation, that's why we get all those zeros. So you can call that 3. And then for y, it equals -8. So we have another local minimum at the point 3, -8. So I'm going to go ahead, add a few more lines in here and plot that point. And then we saw earlier that the y-intercept was at 0, -8, so we can plot that point too, just because it never hurts to have a few extra points. And then we can draw our graph. All right. Next example. This time we were given the expanded form of our polynomial function. So again, grab the graphing calculator, type all this information in. And once you have it all typed in, you can go ahead and hit graph. And it looks like -3 is a 0, so let's check it out and let's make sure. So use synthetic division, divide it all out. Carry down, multiply, bring back up, and then add together. Okay, so we actually got a remainder of 2. So that tells us that even though it looked like -3 was a 0, it was not. So let's come back to the graph, and there is a way to kind of verify that. It really looks like it's crossing there, but if we hit second calc, we can select an x value that we want to check out what the y value is. So if we type in x equals -3 and then hit enter, we actually see that it is not a 0. When x equals -3, y equals -2. So we're going to have to estimate what this y value is, or what this x value is. So we can hit trace. And I know it looks like I should be going up or down, but you actually want to go left to right. So we have -3.03, oh, and -3.1. So it's really, really close to -3. We'll call it -3, but it isn't exactly -3. It's close enough for our use, but not exactly -3. So for one x-intercept, we got -3. And we can do the same thing to calculate the second x-intercept. Just keep scrolling over until you get close. And so right now we're at x equals about 1.4, and y equals -1.25 or -1.2. Hit over again, and now we're above the line. So we can approximate that x is about, or our second x-intercept is about 1.5. It's around 1.5, even though it's not exact. So plot the 2 points. And then let's calculate our local maximum and local minimum, or local maxima and local minima. So again, do second calculate. I like working left to right, so I'm going to select minimum first. Come all the way back over here so I know I don't forget something. And it's always, you have to always start with the left bound, so I'm going to get really close and hit enter. Keep going till the y values are going back up, and then hit enter, and then check. So it's about negative 2.3 and about negative 9.5 for one of our local minimum. We'll calculate the local maxima or maximum. I'm going to hit clear so all that information goes away. And then second calculate again, go with the maximum. Always start off with the left bound, so get close to the maximum, but on the left-hand side of it. Once we turn around and start coming back down, we can hit enter again for the right bound and then calculate. So our local maximum is about negative 0.6, negative 3.5. And these are estimates, but they're pretty close, so we can go with those. And then we have one more local minimum to calculate. So we're going to hit clear, second calculate, and then minimum, or you can just hit the number 3, scroll over until you are close but not quite touching the minimum for the left bound. Keep going until your cursor starts going up for the right bound, and then hit enter again for a guess. So for our x value, it's equal to about 0.7, and for our y value, it's about negative 7. So I'm going to estimate this as 0.7, negative 7. We can plot these points. And it's not going to be perfect, but we want to be close. Need to draw in a few more lines here. And then just like what the graph showed us, we can draw the rest of our graph. And then again, this came from an earlier section, this chapter. Does it match what we would expect from the end behavior? Our leading coefficient is positive. So then as x approaches infinity, f of x should also be approaching infinity. And then as x is approaching negative infinity, because we have a degree 4 and 4 is an even number, f of x should be approaching positive infinity. All right, we have just one more example to look at, and for the last example, we're going to focus on what are we supposed to do if our solutions don't quite fit into our window.